In this last video, we're going to take a look at how the binomial theorem is going to end up getting used in calculus. So I'm taking advantage of this opportunity to review a little bit more the binomial theorem and do one more example with that, but also work in some previous material, way back from chapter 1, where we worked with difference quotients. Now the difference quotient is just this fraction, f of x plus h minus f of x all over h. And here I've drawn a picture to remind us of what that looks like. If I have the graph of some function f of x, now here I have graphed a function that looks somewhat like x to the fourth. Okay. I would have a point on it, x, f of x would be the name of that y value. And then I'd have a nearby point. If this x value is at x, and this x value is at x plus h, I'm essentially letting h represent that horizontal distance between the points. Now in this case, h is a positive number, so it really is a legitimate distance. If h were negative, x plus h would just end up being a point that was on the left, on the other side of x. Okay. So that gives me these 2 points. If I draw in the line connecting them, we call that a secant line, and the slope of that is what this difference quotient is. Slope is just rise over run. The difference in the y values is f of x plus h minus f of x. And the difference in the x values, x plus h minus x, would simplify just to h. So anytime we're simplifying this difference quotient, we're really simplifying the slope of a line. And what you do in calculus is you're going to let h get smaller and smaller and smaller, so that you're looking at points that are getting closer and closer and closer together, so that you're trying to see what's the slope of the line that really matches the quote-unquote slope of the function at that particular point. So part of that involves working with these difference quotients. Okay, so let's work this through. So part A says to use the binomial theorem to evaluate f of x plus h. Well, if f of x was x to the fourth, remember x is just a placeholder for my input. So whatever my input is goes inside these parentheses and gets raised to the fourth power. So f of x plus h would simply be x plus h raised to the fourth power. So that is a binomial raised to the fourth power. So I can evaluate that using the binomial theorem. My terms are just x's and h's. So I'm going to have some terms where I've got all 4 of my factors are x's, so x to the fourth, plus some terms where I've got 1 less x, which means 1 more h, plus some terms with just 2 x's, but then 2 h's, plus 1 less x would be x to the first, 1 more h would be h cubed, plus somewhere I don't have any x's at all, but all 4 factors would be h's. So these are the types of terms that I would have, and to get the coefficients, I'm just going to use Pascal's triangle. So the coefficients that I'm filling in are 1, 4, 6, 4, 1. So that's it. There really isn't any simplifying to do because there weren't any numbers that showed up in parts of these terms, and each was just a variable to the first power. So that's part A. So now if we want to work out our difference quotient, and I have these words here, record restrictions. I'll remind you in a moment of what I mean by that. So f of x plus h minus f of x over h. In simplifying this, my goal is almost always to get to the point where I can factor out an h on the top so that I can cancel that h on the bottom. Now, as long as h is on the bottom, I can see that it's not allowed to be 0. As soon as I cancel it, I need to record that restriction that h is not allowed to be 0. All right. So f of x plus h, that's what we just got right here. That's x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth. That, all of that is my f of x plus h. Now I need to subtract from that f of x. And f of x, remember, was just x to the fourth. And then all of that is over h. Now, there's an x to the fourth, and there's a negative x to the fourth. So those are going to cancel each other out. And then all of these terms that are left on the top have at least one factor of h in them. So I can factor out an h on the top. That's going to leave me with 4x cubed plus 6x squared h, because I pulled one of those h's out, plus 4xh squared, again, I pulled one of those h's out, plus h cubed. And that's all over h. Now, with an h on top and bottom, I can cancel it as long as I record that h can't be 0. So I can say this is the same as 4x cubed plus 6x squared h plus 4xh squared plus h cubed, with the restriction that h is not 0. I need to record that because the original expression is not defined if h is 0. This, if I don't record the restriction, would be perfectly well defined if h was equal to 0, but I want it to equal this thing which isn't defined. So I have to record that restriction if I'm going to say that they're actually equal. All right, so that is a little bit of a review of the binomial theorem and sort of a preview of how you'll be using that to work with these difference quotients in calculus next semester. And then you'll go even further in calculus, but we won't go into that this semester.